Today I am going to talk about inductors in AC circuits. If you haven't already seen my video on capacitors in AC circuits, you need to watch that. I have it linked below in the description and up here. And I'm going to use that video to help me explain inductors because at any moment in time, an inductor is going to be acting opposite to the way a capacitor will act under the same exact conditions. So let's take a look at that by showing my demonstration circuit to explain how a capacitor works in DC and use an inductor instead. So there's my battery, here's my switch, a resistor, and now an inductor. Back to the battery. And I really don't need the discharge switch because of the nature of an inductor, so I'll leave that out. So I'm going to close this switch. And what happened with the capacitor? I had a surge of current into the capacitor, and that built up charge on one of the plates, which drove charge off the other plate. So current went in, the same amount of current comes out, looks for all intents and purposes like a short circuit. What does the inductor do at that moment in time? Well, a surge of current tries to go into the inductor. That current creates a magnetic field. That magnetic field is getting stronger and generates a current pushing in the opposite direction that pushes as strong as the current coming in. In fact, it's possible to even be stronger, but we'll just say it's as strong as the current coming in. So current tries to come in, current pushes back, and so we get no current through the inductor. So at the moment we threw the switch with the capacitor looked like a short circuit, but the inductor looks like an open circuit. Now as time goes by, that magnetic field is going to build and it's going to slow down. It's going to build slower and slower, and as that slows down, it's going to generate less current, and so it's going to start allowing some current to go in there. And so as time goes by, more and more current goes in. That magnetic field is building, but it's building slower and slower, and eventually we get an equilibrium where we have our maximum current flowing through the inductor, and now that the current is no longer increasing, the magnetic field is no longer increasing and is now stable, and that magnetic field has to be changing to have an effect on the current. So when we have current pushing into the inductor, that magnetic field is increasing, it pushes back, but when it stops increasing, it is no longer pushing back. And at that point, this inductor looks like exactly what it is, a piece of wire. So current is flowing through it as freely as the resistance in that wire will allow it. So let's say this inductor has, for whatever, it depends on the inductor, let's just say it has 1 ohm of resistance. And let's say this is 1 volt. So that's a 1 ohm resistor. Well, now at this point we are going to have 2 ohms, 1 volt, so we're going to have 0.5 amps of current flowing through that inductor. And then when I open the switch, what's going to happen? The current is going to attempt to stop. You know what? I'm going to put that other switch here just to avoid a certain complication that I'll explain in a moment. Because what's going to happen is that magnetic field is now going to collapse, or at least get weaker. I use the metaphor of a building and collapsing magnetic field, which is commonly used in the electronics industry. And I know that it's really not building and collapsing, it's getting stronger and weaker, but I'm going to stick with the typical metaphor of building and collapsing because it's a little easier to follow in your mind. So that magnetic field is collapsing, it's getting weaker, and so what's going to happen now, as it's collapsing, it's going to generate a current in the same direction. So when we pushed current in, it built a magnetic field which generated a current which pushed back. Now, as that magnetic field collapses, it's pushing in the same direction. So at first, we try to put current into it. It says, no, you're not either. I'm an open circuit. But after a while, it looked like a short circuit, except for the resistance in the inductor. Now it is pushing current in the same direction. And the reason I need to put the switch here now, which I just realized, is in reality, we don't have to be realistic, but in reality, that magnetic field collapsing is going to generate enough energy that it could cause a spark across the switch. I guess not a big deal, but we'll deal with that now. So I'll close this switch so we simply get a current flowing in this direction. And so that magnetic field is going to generate a current. It's going to collapse very fast at first, but then slow down, slow down, slow down, and eventually the magnetic field is gone. It's no longer generating any current, and we're back to where we started. And I'll go ahead and open this switch and open that one, and we're back where we started. And another interesting thing to look at is the voltage polarity across the inductor. Remember that when the capacitor was charging, current was flowing this way. Then when it discharged, current flowed the opposite way, and I refer to that as negative current. Current flowing this way was positive current. Current flowing the other way was negative current. In the inductor, we get something similar. Well, I don't know if you can call it similar, but the concept works out the same. When current is flowing into the inductor and it's pushing back, it's acting like a resistor. And what do we get when we push conventional current into a resistance or any kind of a impedance? We're going to get a backup of voltage where it enters that impedance, and so that's going to be our positive side as our voltage is stronger there, and our negative side here. So higher voltage here and lower voltage there. Higher voltage is always where the current enters the resistor, or in this case the inductor. But when we open those switches, or open the charging switch, if we can call it that, and then close this switch, and the current continues to flow the same direction, now we have energy in that inductor that's being imparted into the circuit. So now this is a power source. And conventional current comes out of a power source. Where? On the positive side. So we get a sudden reversal of polarity. So while the current is going in there, this is the polarity. Goes in, stabilizes, then we get no voltage at all. Then when I open that switch, that magnetic field collapses. Now it's pushing current out that way, and what do we get? Positive to negative. So the voltage across that inductor reverses. Let's take a look at the graph of how this looks. So here's our time, and for right now this will be voltage, and it'll be current too. So with the capacitor, what happened at time 0? We had 0 volts, and I'll use red for our current, 0 volts and our maximum current, and we had the voltage climb up in a curve that looked like that, and our current dropped in a curve that looked like that. That was the capacitor. Now, what's the inductor going to do? It's going to be exactly the opposite. So at the moment we throw that switch, we get our maximum voltage because it pushes back maximum there. So there's our maximum voltage. But as time goes by, that voltage is going to drop, eventually down to 0. Once that magnetic field is completely built and is no longer moving, the voltage across the inductor is 0. It's no longer pushing back. But what happens to the current? At first, of course, it's pushing back. Looks like an open circuit, so we get 0 amps of current. But as time goes by, the current gets higher and higher and higher as that magnetic field stabilizes and stops moving. It allows more and more current to go through. And so now we have our maximum current and our, well, a voltage of 0. So remember, with the capacitor, we had our voltage go up to maximum and our current started high and went down to 0. With the inductor, we get our current is at 0, our voltage is maximum, our current climbs up to its maximum, and our voltage drops down to 0. So it's exactly the opposite of what the capacitor does. Now let's start flipping that switch back and forth, and remember what happened with the capacitor when we did that. Here's our 0 voltage line, and the capacitor would charge, discharge, charge, discharge. And the current across that capacitor would jump to a high current, start to go down, but as soon as I changed the switches and started discharging the capacitor, the current would jump to a negative current, start to go down. And then when I changed the switches again, went to charge the capacitor, it would jump to a high positive current as it charged. But then when I flipped the switch, it would jump down to a negative current and be discharging. And notice that the faster I flip that switch, the more time it spends in a high current state. So if I flip the switches slowly, I would get something like this. I would get a charge, and then the current across the capacitor would go down, And then notice how much lower the current went than when I flipped the switch. It goes to a high state and then slowly goes down. So notice I get less current as time goes by. So if I flip the switch fast or quickly at a high frequency, I spend more time in a high current state and I don't have time to go to a low current state. But if I flip the switch slowly, it has time to go to a low current state. So the faster I flip the switch, the more current I got through the capacitor. So at a higher frequency, the capacitor looked like a smaller resistor. High frequency, more current. Low frequency, less current. So remember that capacitor acted sort of like, and I do emphasize sort of, acted sort of like a resistor that had less resistance at high frequencies and more resistance at low frequencies. And remember we had a formula to calculate what that was. Our capacitive reactance is equal to the reciprocal of 2 pi times the frequency. So that's how fast I'm flipping that switch. And really, we're talking about sine waves here, so this would be at a particular frequency. And then the capacitance. And remember, we have to take the reciprocal because the current through the capacitor is a reciprocal of the frequency. So that's the formula for the capacitance. But in the case of the inductor, let's show how the inductor works. Here is our zero line again. It's going to look the same, but this time it's going to be the opposite entities. So I flip the switch, I get a high voltage, and then that voltage comes down. Flip the switch again, I get a reverse in polarity, and then the voltage comes down. So this is the voltage that's reversing polarity now, as I showed before. So in the capacitor, it was the current that reversed polarity, which current flows this way, current flows that way. That was opposite polarities, or negative current. This time it's the voltage, as I showed before. That voltage on the inductor flips. When the current is going in, the voltage is one way, but when it is pushing the current in the same direction, the voltage flipped. And that's what's happening here. So as I flip those switches, I get voltage that does this, not the current. And now the current, what's the current doing? The current is going to climb up, and then the current's going to go down. Current's going to climb up, the current's going the same direction, so you don't get a reverse in current, and then the current's going to go down. So as I have a lower frequency, it takes a while for the current to go up. Now if I have a very low frequency, voltage is going to drop very low, and the current is going to go much higher. Kind of crude there, but you can see it. So if I do it slowly, the voltage is going to go down and the current's going to go up. But if I change it fast, the voltage goes down, the current doesn't go as high. And let's flip that switch really fast now. Here's my zero line, and now my voltage is going to go up, come down a little bit, go negative, come down a little bit, go up, come down a little bit, go negative, come down a little bit. But my current is not going to get a chance to get very high. My current's going to come up a little and then go back down. Come up a little and then go back down. So if I flip it quickly, I don't get much current. If I flip it slowly, my current has a chance to come up and become a high current. And if I flip it real slow, it's going to stay in a high current state. But if I keep flipping it back and forth, my current never gets a chance to get very high. So at the higher frequencies, I get less current. At lower frequencies, I get more current, just the opposite of the capacitor. So the capacitor passed more current at high frequencies, but the inductor passes more current at low frequencies, so just the opposite. And so there is a formula to calculate that, just like with the capacitor, but since the current is not the reciprocal of the frequency, it's going to not have the reciprocal in the formula. So my inductive reactance, my X sub L, is simply equal to 2 pi times the frequency times the inductance. And so it's a simpler formula. I don't have to take the reciprocal to find out what the inductor is doing. So that is a shortcut to that. I didn't go through all the explanation of all the curves here. I'll talk about that in just a moment. But to find my inductive reactance is just X sub L equals 2 pi FL. And so we have two entities that act differently. Let's do a little graph of, this time it's going to be frequency instead of time here. So as my frequency goes up, let's use, how about green for a capacitor? So as my frequency goes up, my impedance, or my reactance, I'll just put a little X here, Put that in green. I'll also put it in red because green is going to be my capacitive reactance. I'll put a little C here to remind us. That's my capacitive reactance. Red will be my inductive reactance. So at low frequencies, my capacitive reactance starts high reactance, little current. And as my frequency goes up, my capacitive reactance comes down. So higher frequency, less capacitive reactance, fewer ohms. With the inductor, just the opposite. At low frequencies, I have a low inductive reactance, and as my frequency goes up, my inductive reactance goes up. So they act exactly opposite to each other. So I showed at the different stages of the charge and discharge cycle, they acted exactly opposite. Where the capacitor was a short circuit, the inductor looked like an open circuit. I first closed the switch, the capacitor looks like a short circuit, but the inductor looks like an open circuit. After time goes by, the capacitor looks like an open circuit, but then the inductor looks like a closed circuit, except for the resistance that's in the inductor itself. And here we have the opposite characteristics, whereas my frequency goes up, my capacitive reactance goes down, and my inductive reactance goes up. Now let's take a look at the voltages and currents in the circuit. So let's draw our battery here again. There's our switch, our resistor, our inductor, and back here. So when I close the switch, recall what happens. Surge of current, inductor pushes back, so I get my maximum voltage. And I get very little current. So if I draw my graph here again, at the moment I throw that switch, I have, using red for current again, I have almost no current. I have zero current. At the moment we flip the switch, there's a little bit of a ramp up time that you can see on an oscilloscope, but very quickly I get no current, and then my voltage is going to be at its maximum. So at the moment I flip the switch, zero current, maximum voltage. But as time goes by, that voltage is going to come down. As that magnetic field stabilizes, the voltage disappears because that magnetic field has to be changing to get voltage. When it stops changing, I no longer have voltage pushing back. And then my current, as I have less and less voltage pushing back, my current climbs up. So first we have voltage, and then we have current. So remember, in the capacitor, first we had current and then we had voltage. In the inductor, first we have voltage and then we have current. So once again, they act exactly opposite. And there's an acronym, if you will, to remember what these are. So in an inductor, the voltage comes before the current in an inductor. And in a capacitor, the current comes before the voltage. So we have ELI, or Eli, to remember that the voltage comes before the current in an inductor, and then ICE, ICE, to remember that the current comes before the voltage in the capacitor. And so just remember Eli, the Iceman. So Eli, the Iceman, they should have called the Iceman Eli instead of Etsy is what they called him, the guy they found in the Alps. They should have called him Eli. For Eli, the Iceman, remember that. ELI, voltage comes before current in an inductor. ICE, current comes before voltage in a capacitor. Now let's take a quick look at the relationship between the voltage and the current, as I did in the capacitors, just to see how things line up. Remember that in the capacitive circuit, we had a phase angle because of the delay in time it takes for the capacitor to charge compared to the source voltage. So as we watch the capacitor charge, we see that as long as the source voltage was higher than the capacitor voltage, the capacitor was charging. It was playing catch-up. Now here we see that the source voltage is starting to drop, but it is still higher than the capacitor voltage, so the capacitor is still charging. But when the source voltage meets the capacitor voltage, after that the source voltage is lower than the capacitor voltage, so the capacitor is discharging. So the capacitor voltage peaks when it meets the source voltage. To find the current, we simply have to subtract 90 degrees from that, because the current through the capacitor will always peak 90 degrees before the voltage across the capacitor. So the phase angle was the angle where the capacitor voltage crosses the source voltage minus 90 degrees. In the inductive circuit, we don't have anything quite so intuitive to follow. I mean, we could look at the inductor voltage and see that as long as the source voltage is below the inductor voltage will be increasing. But once the source voltage is higher than the inductor voltage will be decreasing. And so we have a peak right where the inductor voltage crosses the source voltage. And 90 degrees after that will be the peak of the current. But let's see if we can find something a little easier to follow. If we watch the voltage across the resistor, that will be in phase with the current, because just like the capacitive circuit, the current through the circuit is determined by the voltage across the resistor. So when this voltage across the resistor peaks, so will the current peak. So when is that voltage going to peak? Well, remember, according to Kirchhoff's voltage law, the voltage across the inductor plus the voltage across the resistor must add up to the source voltage at any moment in time. Now we have all these curves going all over the place, but if we freeze time, we will see that the inductor voltage and the resistor voltage at that moment in time will add up to the source voltage. So according to Kirchhoff's voltage law, if the resistor voltage equals the source voltage, there's no voltage left over for the inductor. So at that moment in time, the inductor has 0 volts, which is also the moment at which we have peak current in the system. So if we follow the voltage across that resistor, we see that as long as the source voltage is higher than that voltage is increasing. But when the source voltage meets the resistor voltage, which is the moment that we have 0 volts across the inductor, we also have our peak current. And once that source voltage meets the resistor voltage starts to decrease. So that's the point where we have the peak of the resistor voltage. And we find that in this circuit with 60 hertz, 30 ohms, and 100 millihenries, that is going to happen 51.4 degrees after the source voltage peaks. So we have the source voltage peaks, add 51.4 degrees. Now we go straight down, and that's where the current is going to peak. So that's going to be our phase angle right there. The current peaks 51.47 degrees after the source voltage peaks. And of course, the voltage across the inductor will peak 90 degrees before that, but we're not interested in that in the inductive circuit. We just want to see where the current peaks, and that will be at that particular point. So once again, we can see that there's a reason why the voltage comes before the current and why the current lines up the way it does and why we have finally a phase angle, but it's a lot easier to calculate it than to draw it out on a graph. So let's take another practical circuit. I'm going to have a AC source. We will make this 50 volts at 60 hertz, just like we did with the capacitor. This will go through a resistor and then an inductor. And just like with the capacitor, let's make this a 30 ohm resistor. And let's make this a 100 millihenry inductor. So we had a 100 microfarad capacitor. We'll use a 100 millihenry inductor because I like the way the numbers come out with that. So what we need to do to find out what the entire effect of this circuit is, of course, is to find out what the inductive reactance is at that frequency. So let's go ahead and figure that out. I'll pull out my trusty calculator. And before I do that, let's remember what the formula is. So for a capacitor, it was 1 over 2 pi Fc. For an inductor, the X sub L, the inductive reactance, is simply equal to 2 pi Fl. And so what we have here, I'll just put the numbers right here, 2 pi, which is 6.28, times the frequency, which is 60 hertz, times the inductance, which is 100 millihenries, which will be 0.1 henries. And so we simply multiply those together. So we have 6.28 times 60 times 0.1 equals, and we get 37.68 ohms. For the inductive reactance. So I'll put that right here, 37.68 ohms. Now, can I just add those together? No, because once again, there's a phase angle involved. The current through the circuit is behind the voltage, so they don't add directly. I have to add them using the Pythagorean theorem. And I'll remind us how that works. We start out by drawing a horizontal line which represents our resistance. So there's 30 units there to represent our resistance in ohms. And then we have a vertical line that's going to be a little longer because that represents 37.68 units of inductive reactance. Now remember, I said that when we did the capacitor, I drew the angles the same way, but I really should have drawn the horizontal line. The capacitive reactance should have gone down. That's just by convention, because our capacitive reactance acts opposite to our inductive reactance. So by convention, inductive reactance will go up and capacitive reactance will go down. So this time I'm doing it right to begin with. So I just need to find out what the hypotenuse of this triangle is to know what the actual impedance is. And of course I use the Pythagorean theorem, which means I square this and square that, add them together, take the square root, and I get the answer. So what I need to do is take 37.68, and I'm going to square that, store it away. Now I'm going to take 30, square that, add it to the square of that. Now I have a useless number, but I'm going to take the square root, and I got 48.16. So our impedance, or the length of this hypotenuse, is going to be 48.2 ohms, 48.16 ohms. But that's only half of the answer, because we also want to know how much our voltage is leading our current in the circuit, and that's going to be this angle right here. So the timing that the voltage leads the current, which we convert into an angle, is going to be equal to this angle right here. So how do we calculate that angle? Once again, a simple trigonometric function. We take our reactance and divide it by our resistance. Then we just take the arctangent of that. So the formula once again is our arctangent of our inductive reactance divided by our resistance. And that's going to be 37.68 divided by 30. So, very simple, 37.68 divided by 30 equals, I take the arctangent of that. So I find my tangent function, take the inverse of that, or the reciprocal, whichever way you see that. And I got an angle of 51.47. Let's make that 51, just make that 51.5 degrees. So there is our angle, and 51.5 degrees for that angle. So now we calculated the total impedance of this circuit. How does the inductive reactance and the resistance add together to give us a total impedance? So together they're going to act like a 48.2 ohm resistor at that frequency. And how much does the voltage lead the current? It's going to be by 51.5 degrees. And how do we express that? Let's go ahead and write this right up here. So our impedance is 48.2 ohms with a phase angle of 51.5 degrees. And so that is the total action of the circuit, telling us once again that our 37.68 ohms of inductive reactance combined with our 30 ohms of resistance is going to act like a 48.2 ohm resistor, and our voltage is going to lead our current in the whole circuit by 51.5 degrees. And to put this in rectangular notation, as you recall from the capacitor, let me get this out of the way. So the rectangular notation once again describes the triangle, so I'll just draw that again quickly right here. 30 ohms and 37.68 ohms. So the rectangular notation is going to be, just put it right here, 30 plus J. Remember the capacitance was minus J because we go down. Now we're going to go up, so that's a plus J, 37.68. So the rectangular notation using the complex number, which as you may recall, if you know your math, our complex number, this should be an I, but in electronics, I represents alternating current. So we use a J, and this will represent the base and the side of that triangle, And then, of course, we can use those numbers to calculate the hypotenuse. So that is going to be rectangular notation, and that is polar notation for the same circuit. So just a quick review of how this works. Let's get these out of the way for a moment. I'll leave these numbers here. First thing we need to do to calculate how this inductor reacts in this particular circuit, we need to know the frequency and the inductance, and then we can plug it into this formula. Our inductive reactance is equal to 2 pi times our frequency times our inductance. So that's going to be 6.28 times 60 times 0.1 will give us 37.68 ohms. And to see how that works together with the resistor, we use the Pythagorean theorem. Square that, add them together, take the square root is going to give us the hypotenuse of this triangle. That'll give us the length of this triangle, and then we take this, divide it by that, take the arctangent, and that gives us the angle, and that tells us what we want to know about that circuit. So that is how inductors act in alternating current. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.